All right, we got about 5 minutes before we'll get started. Let's see if we get any more people.
Hello, can you hear me?
Yep.
Okay, good. I can hear you. And maybe put a shout out to everyone else. Be sure they can hear you.
Yeah, can everyone see my screen? And also, are they able to hear me? Because that would be good if everyone could.
Okay, you got a bunch of yeses, so you can start in 3 minutes.
Sounds good. All right. Just about to get started here. Let's see, how many we got? 14. Okay. Today we're going to be looking at a lot of different things you can do with various libraries that are important in statistics. So we'll look at things like mean and some averages, different ways you can do the same thing, either through brute force Python or for different libraries. So let's get right into that. So a fundamental part of working with data is being able to describe it. And what are called descriptive statistics help simplify and summarize a large amount of data in a sensible manner. We're going to talk about how This covers a bunch of methods for summarizing, describing, and representing data sets. And if you want some more information, these are some good links. Real Python's pretty good. I haven't seen this specific one, but I'm sure it's fine. So let's recall an example that you guys had in the lesson about highest grossing movies. And we're going to look at some things we can do with that. So first thing we're going to do is we've got a piece of code here. And what it's going to do is we're going to be given a URL, and we're going to use the get from requests to get the data from there, open it, and write it to a local file. Now, I already tinkered around with this, but you can still run it and it'll be fine. So let's run that. And we're going to be using numpy and pandas right now. And the first thing we're going to do is we're going to read our CSV file. And we're going to take a look. Okay. So what are we looking at here? We've got a CSV read into pandas. We've got columns of the movie name, the director, the year, the budget, and the gross it made. Okay, that's pretty cool. It's all set up for us in a nice table here. First thing we're going to be looking at is what are called measures of central tendency. This gives us an estimate of the center of a distribution and a sense of a typical value we'd expect to see. The three major measures we're going to include are the mean, median, and mode. So the mean is probably the one you're most familiar with. You probably talk about the average a lot. So given a bunch of values, sum them together, and then divide by how many values you have, and that'll get you what your standard mean usually is. The question is Dr. Cleveland going to host a review session for the test tomorrow? I don't know. I'll probably let questions like that happen once we're done here. Okay, so there are actually a couple different kinds of means. The one we're all used to is called, what is it called? I was just reading this earlier. It's called the arithmetic mean, is the one we're all used to. Oh, it's right in front of me. So the arithmetic mean, also known as the average, is the sum of all the values divided by the number. So we're going to sum from I equals 1 to n, and then divide the resulting sum by n, and that will give us the average of our collection here. So this is the one you're probably used to using. It's probably the most applicable in everyday life. So let's see what we can do with that. What we want to do is calculate the average budget of the top 10 highest grossing films. So first thing we're going to do, we have our movies stored, and we can access the column of budget underscore million, which is actually the name of the column. There's no fancy characters in here. It's just the string of the column name. And what we get is the values in that column. So we have the budgets for the 10 highest grossing films. Here's the name of the column, and its type is float64. It's just the way the data was stored in is that they were floats. So this is in millions of dollars. But so we can use just Python, all the primitives and the built-ins to calculate what we want. And what we want is the arithmetic mean. So how do we get the arithmetic mean? Does anyone remember how we get the arithmetic mean? Just in terms of the things you can normally do in Python.
Could you add up all the elements and divide by the number of elements?
That is indeed what we're going to do. So instead of doing like a hard code, add this plus this plus this plus this, what we do is we make a list with all the elements. Now we could make this list from this using a Pandas library, but the idea is to not use any libraries. So we're going to make a list with all our values, and then we're going to take the sum of that list, and then we're going to divide that by the length of that list. So what that gets us is 115.66 million USD. That is the average budget. So the average of these 10 numbers here is going to be, so you take 3.9, add it to 237, so on and so forth, and then you divide it by 10, which will get us this. We can always, or we can also use our external libraries to do the mean. It's pretty easy. Almost all of them have the mean keyword to represent this. So we can do straight from the Pandas library. We made our, we got our column here, and we do budget.mean, and it is a method. So we do need the parentheses here, but it doesn't take an argument. The average budget is 115.66, same as we had before. We can do the same thing with numpy, but this time, so Pandas is the thing in charge of making the data frames and stuff that we want to store data in. So we can dot right off of budget and do the mean. If we want to use numpy, we need to call the numpy's mean method, and it takes a data frame as an argument. So we're going to do numpy. This is what we made an alias for, numpy.mean, and it takes one argument, which is the data frame we're interested in, and it's the same value. And we can also use the statistics library to do the same thing. So pretty simple, pretty straightforward. We also have what is called the harmonic mean. This is not used as often, and what it is, it's a little hard to read that. You take the sum of reciprocals. So if you think about the regular mean, you're going to be adding all of your items up, and then at the end, you're going to divide by the number. I guess I shouldn't use this symbol here. X. You're going to use everything from I equals 1 to n. You're going to add them all up, and then you're going to divide by n. So I'm just going to divide or add up all my items n times, and then I'm going to divide by n. So you can kind of view this as do an operation and then divide by something. Well, that operation is just take your item and do it n times, and then the division is going to be n. Well, the harmonic mean is, I'm going to write it in a way that if you have a number, let's say x, the reciprocal of that is 1 over x. So what we're going to do is we're going to take the sum of reciprocals, which is going to be 1 over our x, and then we're going to have our normal division. But this whole thing, we want the reciprocal of that. So it turns out being n over, oops, that's backwards. Oh well, the sum of the reciprocal. It's not nearly as oftenly used. Something it's good for is calculating resistances in the system, like electrical resistance. But it's less important that you know how it works, and more important that you know that we can calculate it. So in primitive Python, we're going to calculate just what I said. We've got n, which is going to be the length, and we're going to do the sum of everything in our collection, and we're going to make a reciprocal of that. So 1 over the sum of everything, and then take the reciprocal of the whole thing. And that gets us the harmonic mean. And what we want to do is round that to 2 decimal places. And then using statistics, we've got the harmonic mean. round that to 2 decimal places. And with the, and I'm not sure how to pronounce this exactly, I'll call it Skippy for now. It has a harmonic mean built in also. So let's see. The harmonic mean for our top 10 highest grossing films of the budget, of course, is 13.38 million. The important thing is that they all have the same value. Now, out of just sheer curiosity, what happens? What might be the difference in any of these if we don't round them? Well, let's look. It looks like the Skippy and the statistics library are doing the exact same calculation for as far as we can see. And what we came up with is so close as to be completely negligible. These may as well be the same thing. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is beyond a billionth of a point. So these are probably doing something faster than this. And if I'd remembered, I would have done the clock thing so we can see how fast they each take, but not really that relevant. If you ever need to do the harmonic mean, here you go. And this all works in a data frame, or these two do at least. Next thing we can look at is the geometric mean. This one is much more commonly used than the harmonic. So generally, I suppose in any STEM education, the things you're going to need to know is that there exists a arithmetic mean, which is take the sum of everything and then divide. And then there's the geometric mean. So the arithmetic mean is add stuff together. And so when you add a whole bunch of things together, what is going to be the appropriate thing to do with the length of how many you have? Well, the appropriate thing to do is divide. Well, in the geometric mean, I'm not adding, I'm multiplying. So if I take all n of my items and multiply them together, can anyone tell me what the appropriate thing to do here instead of divide? Because it's not divide. Division isn't powerful enough if I'm multiplying instead of dividing or instead of adding. So Dylan says square root, very close. It is the nth root. So if I add 3 things together, I want the cube root. I'm sorry, if I multiply 3 things together, I want the cube root. If I have 4 things I'm multiplying together, I want the 4th root. I think that's how you articulate that. But yeah, so in a normal sum or a normal average, I divide. In the geometric mean, you take the nth root. What is it good for? Well, this one I actually know quite well. So when you're talking about the geometric mean, which I'll just represent, the arithmetic mean, I'll just represent like this. It's when you've got a relation of something that is somewhat linear or at best polynomial. So I can talk about the average thing that goes on here. So think of any, like you go to work, you get paid, you come back, and then you tally your income versus expenses for the year, right? You can calculate your average per day, and that'll be good for this one because the amount you made yesterday doesn't really affect so much the amount you have today. And the amount you have in your bank doesn't affect so much what you're going to make today. But when you're looking at things that have an exponential growth pattern, you're going to be talking about the geometric mean instead. So the classic example is you got a bunch of plants, and this works with viruses too. Anything that has exponential growth. I've got a plot of land, I put down 100 seeds, and let's say they all grow. And I want to calculate what my average expected number of trees are going to be. Well, if I take the arithmetic mean, let's say every tree on average, for every 10 trees, I get a new one. So that means I'm going to get 10 and this year, and then I'll get 11 the year after that, and then so on and so forth. Well, it turns out you get a little more than that. And that's because you're not taking into account every time I get a new tree, I'm increasing the amount of things that can possibly give me a new tree. And so when you have something that reproduces like that, or a virus, so 2 becomes 4, becomes 8, so on and so forth, the geometric mean is what you want to work with. So the arithmetic and the geometric mean, very useful. You'll use them all the time. Harmonic, I can say outside of just learning it and stuff, I've never used it. Okay, so how are we going to compute the geometric mean? Well, very similar to what we were talking about before in primitive Python. We're going to make a list, put all of our stuff in there. And what we're going to do is, I think there might be a product just as there is the sum, but this is the behind the scenes for us. Here, this is the behind the scenes code for a sum. Oops. Take everything in my list. And I've got a starting thing, and this will be 0. So it takes 0, and I add the first and the second and third, fourth, fifth, so on and so forth. That's how sum works. This is how the product function would work. Anybody tell me why this needs to be 1 instead of 0? The number we're starting with to keep track of our product is 1. Why is that?
Maybe because if you multiply anything by 0, it's 0.
That's correct. The true answer is that 1 is the identity for multiplication, meaning the identity for any operation is take a number in my operation and the identity. So number, an operation, and the identity is going to give me the number. For addition, it's 0. Oops, it needs to be a y. And so the reason it starts out is this always starts out as the identity, meaning that an empty sum is going to be 0, and an empty product is going to be 1. Okay, so we start out with 1, and then we multiply everything together. And then what we do is we're going to take the whole thing to the power of 1 over our length. So that gets us the root of however long it is. And we're going to round that to 2 decimal places. And as with before, statistics and Scipy just have this function built in. So let's see what we get. So we get 34.96 million USD. Okay, let's see what happens if we don't round these. They're out to the like trillions. They're pretty much the same thing. Okay, so those are the means, at least the ones we'll be talking about. The next one we're going to look at is called the median. Median is going to be the middle element of a sorted data set. The value where the upper half of the data lies above it and the lower half lies below it. In other words, it's the middle. To calculate the median, arrange the data points in an order, and the middle value is the median. If the number of elements is odd, then the median is the value of the middle position. If it's even, then it's the arithmetic mean of the 2 values in the middle. Now, can you calculate the mean of a data set if it is not sorted and can't be sorted? Let's say I have a data set of Jim, Larry, and Bob. What's the median of that data set? Why would you say Larry? It's fine as guess as any. I think I know why you guessed Larry, but I would like to hear why you guessed Larry. My guess is because he's the person in the middle of the order. 1, 2, 3. The issue is there is no median for that data set because there's no order to them. So without an ordering on my elements, I can't tell you what the one in the middle is. I can't actually tell you what the average is either. Now, if I were to tell you that it needs to be ordered alphabetically or in order of appearance, then we can start. But you can't calculate the median of a data set if there's no order to it. Okay, so let's use primitive Python to calculate the median of a set of numbers. And with numbers, the order is pretty straightforward. Okay, so we have our list. We want the length of it. If n is going to be even, let's see. I think this is going to be shorthand for mod. This is equal to 0. So we're going to have the sorted list, and we're going to divide it in half and get the element we want. So we're calculating the index here. No, this is going to be odd, I guess. Right. Okay. So the reason this works is because there's a strange behavior in that if this is equal to 1, this is the same thing as being true. So 1 and true evaluate to the same thing. So this says if n modulo 2 is equal to 1, meaning it's odd. So we have our sorted list. And which part do we want? We want the one in the middle. So what we do is we know it's odd. So if we divide it by 2, we're not going to get what we want. But if I subtract 1, now I know I'm going to get an element. So that's going to be the element in the exact middle for the odd list. Otherwise, what we're going to do is get the average. I wonder why that's red. Get the average of the. You've got the middle 2 elements. So I've got the one on the left, one on the right, add them together and divide by 2. Okay. So the median, meaning the value in the middle, for our highest grossing films is going to be 2,673 in millions of dollars. You can also use your external libraries. We've got our pandas, numpy, statistics, and I don't see scipy in here, but that's fine. We calculate them all. We also have the ability to, if we have an even number, we can see what the low median is, meaning instead of taking the average, you take the lower one, and you've got the high median, which is the one which is higher. Main difference between behavior of the mean and the median is related to data set outliers or extremes. Mean is heavily affected by outliers, but the median only depends on outliers either slightly or not at all. So if I have items like this, my average is going to be here in the middle. But if I have items like this, my average is going to be pushed way down, whereas the median is going to be pushed down a lot less. Let's take a look at something that might show that out. We're going to replace the value of 3706, which was the gross in millions for one of these. And we're going to replace it with, what is this going to be? 99,000, which is, it's a lot of money. It's, I would make a topical joke, but yeah, that would be depressing. All right, so before we've got our mean of the new gross, and we've got our median of the new gross. So our new mean is what we have here. So it's going to be 12,400, and the new median is going to be 2,673. So then the median didn't change much, if nothing at all, and the mean changed a lot. The mean was here. So that's a lot. The other common one you see, at least from what I remember back in undergrad, is called the mode. And this is going to be the item you see most often. So if you got a whole bunch of stuff, count how many times each different number occurs. And the one that occurs the most is called the mode. So what we're going to do, if we want to do this ourselves, is we're going to take the maximum of every item in our list, take the count, and get the maximum. And it's possible that there could be more than one. So just take one. This is getting to the last one. If we don't put this here, if we don't put the 1, I'll show you what we get. And you see the libraries here can do the same thing. So the first one shows a number of times it appeared and the number itself. So this is a tuple. We can tell by the parentheses. So 3706 appeared one time, and that appears to be the what that would mean is all the items are unique. So the maximum count, they're all 1, so it didn't really matter which one it was going to be. So we returned a tuple, and we want the second part of this tuple. That's why we have the 1. So it's not exactly useful when our distribution is flat, meaning the frequencies are similar. It makes more sense when we do not have a numeric value data set, because if this were really, if we didn't measure in millions of dollars, but in regular dollars, you were almost guaranteed to never have two films with the same budget. The distribution is just too flat. However, if we look at the director, it appears that of the highest grossing films here, that the most represented director is James Cameron. There's a South Park joke here, but I'm not good at singing. Okay, so those are what we call the central tendency measures. They show behavior about something in the middle of the data, be either the most common, the item in the middle, or the means, meaning it's hard to talk about the means without saying the word average, because that's what we're all used to saying. Okay. If you want to read some more, here are some more notes on how mode works. And it will be actually useful if you're talking about large amounts of data, especially if the mode is kind of an outlier, meaning if the mode is 6 times as likely as the next level of occurrence, that's unique. That's interesting. Okay, another thing we can talk about is measures of dispersion. What this does is it describes how the data varies. So is our data sparse? It's all over the place. Is it kind of uniform? I don't know. Where does it range from here to there? This is what we're talking about. It's also known as measures of variability. They quantify the spread of data points. The major measures include range, percentiles, quartile range, or quintile, sorry, variance, standard deviation, skewness, and kurtosis. Haven't heard of that one. Variance and standard deviation, you should all be familiar with. I get my labs mixed up, but I do know that some of the homework has hammered you over the head with using these. Okay, let's take a look at the range. What this does is it gives us a quick sense of the spread of the distribution to those who require only a rough indication of data. Where does my stuff range from? The idea is so common that we have the word built straight into our brains. What's the range of the data? Where does it go from? It go from -10 to 500. So we have our data here on the gross. No, wait, this is the budget, sorry. So we take the maximum item, subtract from it the minimum item, and we have the span between them, which is known as the range. And in NumPy, we have a range, and it's the name we have for the function is called peak to peak. So it takes a data frame as an argument, and it gives us the range. So it appears that there is a gap of a maximum gap at $352.1 million in the budget. So the lowest being 3.9, the highest being, what would that be? 356 right there. Range is pretty simple. We can talk about percentiles and quartiles. A measure that indicates the value below which a given percentage of points and data set fall. So this is going to be useful for, let's say you have a test or a practice test or just some task. A good one would be like, there's a hackathon, right? And you've been given a task to make some code, and you submit it, and it's like automatically graded, even though this would be difficult. You get a result back and says you either got it correct or you didn't. Let's say you got it correct, and you scored in the 60th percentile. What does that mean? So it explains it right here. I was just trying to give an example that you might relate to. The sample p percentile is the element of the data set such that everything else are less than or equal to that value. For example, the median represents the 50th percentile, meaning the median is above everything in your, now these generally follow the normal. So everything in your distribution, median is the 50th percentile, meaning everything over here is below the median. Similarly, we can have the 0th percentile representing the minimum and the 100th percentile representing the maximum. Percentile gives the relative position of a particular value within the data set. It also helps in comparing the data sets which have different means and deviations. So we talk about quartiles, which is pretty much what you would expect. We're talking about 25, 50, and 75%. All right, let's take a look at what we can do here. We're going to talk about the budget, and we're going to get the percentile. And the second argument is going to show the 10th percentile. Similarly, we're going to get the 40th and 70th percentiles. And then using pandas, we're going to get the 10th percentile. It looks like it wants a float instead of an actual whole number, which is fine. And with statistics, we can say how many things we want to chunk it into. And the inclusive method, it's less important that you know this one than it is to know this one. Saying how many times we want to chunk it up. Let's take a look. So the 10th percentile is going to be 7.77, so $1 million. So what this means is a budget of 7.77 million means that everything to the left is going to be lower. So, and that point is at the 10% in the distribution we were talking about. Similarly, we can say that 11 is in the 40th percentile. And note that both of these are higher than the 7.77. And another thing that would be worth noting is it depends on how we order this. If we say that we take our budget and we say that the smallest budget is the ideal thing, so it's at the front of the list, or not the front, I would guess this is the best and this is the worst. We could do that, or we could do it either way. So we have the 40th and 70th percentiles here, meaning that if you have a budget of 211 million, then you are higher than 70% of the budget. Similarly, the 10th percentile calculated with a different method, same number. And the quartiles, meaning 25, 50, and 75, are going to be 10.6, So 25 is going to be, I guess we don't have anything close to that, do we? I guess 10.6 is close to 7.7. 25 is kind of close to this one too. The 50th percentile is going to be at 12 million. And then at the 75th percentile, we're at the $22.7.75 million. Another thing was we can talk about the interquartile range. It's the difference between the third and first. Now, this is easiest to describe with a picture. All right, so we have our quartiles. So this is 1, 2, 3. So this is 25, 50, and 75. We want the difference from here and here. And by difference, I mean, it's not exactly this minus this, but it's pretty close. It's not the values that you're subtracting, it's the percentile. Okay, so let's take a look. So if we use numpy and scipy, we get the same thing. The interquartile range, meaning the difference between 3 and 1, is going to be 217.15. If we remember back here, we had 227 and 10.6. So subtract 10.6 from 27.7, and we get somewhere close to 17.1, which is what we have here. Another useful one is called the 5-number summary. It's especially useful in analyses where the preliminary investigation of a large data set. It consists of 5 values, the most extreme ones in the data set, so the minimum, maximum, the lower and upper quartiles, and the median. It can be used to describe any data distribution. It does need to have an order to it, but you always do. And one thing that's useful that visualizes this is called a box plot. We'll see one here, and I think we talk about it a little later too. All right, so let us describe. So when we do this, we're going to list out all the things that the Pandas has deemed as valuable to look at a glance. So let's see, there's 1, 2, 3, 4, 5, 6, 7, 8 values here. The standard deviation and is here, and that's usually not part of this one, but it's fine. How many do we have? 10. What's the mean? It's 115. What's the smallest? It's 3. What's the largest? It's 356. And what are the 3 quartiles? They're here. Pretty useful. Now we can see a box plot here. And what it will do, it shows the range, the interquartile range, median, mode, outliers, and all quartiles. Now, you may have seen this before and wondered what on earth is this thing? Well, now you know. You've got the outliers, which is this one here. It's right there. 5,000 is an outlier. You've got the quartiles. You've got the range, meaning largest minus the smallest. And yeah, it almost 1-to-1 correlates with the 5-number summary we were just talking about. Another thing we have is the variance. We've seen this a lot before. It quantifies the spread of the data. It shows, so we have 2 normal distributions, right? We have that one, and we have that one. I guess this one should look more like that. How smushed is the curve? What's the spread of the data like? It shows numerically how far the data points are from the mean. This could be, it may or may not be meaningful if the data sets are highly spread. So let's calculate the variance for the budgets. Note that if we're working with the entire population and not the sample, the denominator would be n instead of n-1. So what's the difference? Well, let's say, I don't remember how many students we have this year, but last time I did this example, we had about 30,000. Let's say I want to do a study of the students at Texas Tech. Okay, well, turns out my budget's unlimited. I'm going to go ask everybody. I'm going to make it mandatory. Everyone has to answer. That's the entire population. That's incredibly rare in order to actually have that happen. So usually what I do is have a sample. I'm going to get 300 people from our 30,000 population and choose them intelligently and get them to answer my survey. And we would use n-1 instead of n. Okay, let's calculate our variance. So what we have here, we got our stuff. We got the length. We've got the mean, which is the sum divided by the length. And so the variance is going to be, take the sum of the difference between each item and the mean, square that for every item in our list, and then divide that by n-1. Similarly, we can use statistics to get the variance. I'm pretty sure all of these are going to have a variance. Pretty much same thing. Exactly the same thing for as far as we can see. Standard deviation is the other one that you should all be familiar with. It's another measure of data spread. It's connected to the sample variance, as standard deviation S is the positive square root of the sample variance. Standard deviation is often more convenient than the variance because it has the same unit as the data points. So let me see if I can remember this. I'll have to look it up. I don't remember the exact numbers, but I have it in one of my other labs. So we have our distribution, right? And we have the mean. What you can say is, I don't remember the first number, but I do remember the second. So what I'm going to do is I'm going to draw an area around the mean. And this is one standard deviation to either side. And what I can say is that I think 68% of all my stuff falls in this region. Now, my graphic isn't probably to scale, but this is one of the things that standard deviation can tell you, is if I take the mean plus or minus one standard deviation, I get 68% of everything in the distribution. If I take two standard deviations to either side, I get 95%. Meaning that if I get an item that is two standard deviations away from the middle, or away from the mean, there's a 5% chance that it's actually a good data point. So if, let's say I flip a coin, I'm pretty sure at least we talked about this, right? I flip a coin 10 times. That's my study. And I'm going to tell you how many times I got a heads. And I do that 1,000 times. Let's say I return to you a number 9. There's a 5% chance that that coin is fair if I tell you that that number is 9. You can either say, really, that's not the best way to say it. Our hypothesis is that the coin is fair. If I return to you a number 9 saying I flipped this coin 10 times and 9 out of 10 times it was fair, what you can say is that is a 5% chance of being a correct outlier. And with that, we can probably reject our null hypothesis that the coin is fair. So that's what one of the things that standard deviation is very useful for. We can calculate that pretty easily. What's our formula? Well, instead, it's very similar to this one here. We're going to take the sum of our item minus the mean, and we want that to be a positive number. We're going to square the result, divide the whole thing by n, and then take the square root of that. Okay. So we have the same thing going on here. And oh, yeah, it is the same thing, isn't it? The difference being the n is implying we would be using the entire sample in this formula here. So we take the variance formula, sum item minus mean squared over n minus 1. Well, that looks familiar. We just take the square root of that. Okay. So the standard deviation for the budget on the top 10 looks to be 142. So what that would also mean is, what was print? I think I can do budget mean, right? Oops. All right, 115. So if this is 115. If I go to the right by 142, that gets me to what? 257-ish. 257. I go to the left by 142. That can't be right. I need to relearn my statistics. I'm not sure if that's correct. Okay. Another thing we can talk about is the skewness. So not all, well, I suppose I made a grave error here, in that the stuff I was telling you about the to the left and the right, it's correct, but I made a grave error. Can anyone tell me what it was before I spell it out? It has something to do with this here. I made an assumption I never should have made. Someone tell me what I assumed about our data. I drew this figure here. And what kind of distribution does this, what kind of distribution looks like this? Bell curve, good enough. The normal distribution looks like this. I assumed our data was normal. And that is the reason I'm taking time to explain this is this will happen to you. You get so used to your data being the normal distribution because it's so common, that when you assume your data is normal and then you go and subtract the standard deviation, you get a negative number and you're like, wait a minute, that can't be right. I assume the data here is normal, and you can't do that. You can't always assume your data is going to be on the normal distribution. Okay. Next thing we'll talk about is what is known as skewness. And this is what immediately made me remember the problem, is because skewness indicates what where the items are skewed to, right? That's definitely right skewed. That one's left skewed, so on and so forth. There are several mathematical definitions. I'm not sure which one the libraries use. The Fisher-Pearson standardized moment coefficient is calculated by using mean, median, and standard deviation of the data. So I'm assuming that at least one of these is going to do that. I know that we're going to do that, but I'm not sure what the libraries themselves use. So what we're going to do, does this formula look familiar? Okay, well, that's strange. I don't know why they would schedule two labs back on top of each other, but thanks for coming. Okay. We're going to go through the items in our list, add them together, subtract the mean, divide by S here. What's S going to be? It looks like it's still just the number of items, and we're taking, I see. It's easier to explain here in the code. All right, we have our list of items. We have the length of our list. We've got the mean, which is going to be the sum of everything divided by n. We have the variance, which is the same formula we used before. Now we have the standard deviation, which is our variance square rooted. Now, what we're going to do is we're going to take all the items we were just talking about, and we're going to use the standard deviation in there. So we take the sum of each item minus the mean to the third power, and we're going to be multiplying that by n over this value here. So n over n minus 1 times n minus 2. And we have our standard deviation cubed. Why is that? It's because it's right here. So this is 1 over s to the third power. And we're talking about what is on the bottom of this big giant denominator. So we have n minus 1, n minus 2, and s to the third. And this comes from here. Okay, so we're going to calculate that ourselves. And we're also going to use the scipy method and what looks like from just straight pandas. So the skewness of the budget on the top 10 appears to be 0.76. And as we see here, if the skewness is close to 0, then the data set is considered quite symmetrical. Positive skewness corresponds to a longer or flatter tail on the right side. Negative skewness values indicate there's a dominant tail on the left side. So we can easily tinker with this data. How is this data skewed? Well, turns out that there was a budget of negative 900 million bajillion dollars somehow. I guess it doesn't update into these two, but as you can see, the skewness is ridiculously stupidly negative because I added something in here that is deliberately an outlier. If I change this to something huge in the positive direction, now it's skewed so much to the right-hand side that it's utterly insane. But that's how the skewness can change depending on what your data looks like. So this is saying that it's pretty heavily favored on the right-hand side. Kurtosis. That's a strange name. It describes the peakness of the distribution. In other words, it identifies whether the tails of the given distribution contain extreme values. While skewness essentially measures the symmetry of the distribution, kurtosis determines the heaviness of the distribution tails. Okay. So when we talk about peakedness, it's kind of like you would expect. We've got what we would expect a normal distribution that is less peaked than that. All right, so we have our formula here. It is going to be each item minus the mean to the fourth power over the standard deviation to the fourth power divided by n. Seems very simple. If the distribution is tall and thin, it is called a leptokurtic distribution. I'm not sure what the Greek lepto means. And the other one is platykurtic. That's some Greek or Latin or something that I don't know. I'm sure it means peaky and flat or something like that. Plateau, maybe. And lepto, I'm not sure. Anyway, values in a leptokurtic distribution are near the mean or at the extremes. A flat distribution is where they're more moderately spread out. A distribution whose shape is in between them is called a mesokurtic. Now, meso, I do know. Okay, let's take a look. Of our budget, the kurtosis of the budget is negative 1.31. So where do we say what would measure as what? Well, I don't see where it actually says which, but I can find out. I can look right here. Well, I was looking for a quick answer. I didn't quite find one. We know what the kurtosis is. What that means, I will look up here in a bit. Okay. Now we're going to get into doing some examples ourselves. what we're going to do, and it's important that you see the steps we're going to go through and see which parts are important, because when we look at your homework, look at that. It's pretty similar. Okay, so we got a URL. We're going to get that. We're going to open it up. And what we're going to want to do is read our CSV and probably put it into a data frame. So step one, read the file as a data frame and check its first few rows. Well, we luckily have a function that does just that. So let's read it in. You can see it's done reading because your kernel says idle. We're going to use our Pandas library to read this as a CSV, and we're going to get the head. Okay, step one is done. What do we got here? We got distance, origin name, destination name, aircraft group, class, and data source. Makes sense. We're assuming it's air traffic stuff. Okay, what's step two? Use descriptive functions of the Pandas library to learn more about the data frame. Well, what might be a descriptive function? I believe lesson 12 went over exactly what they are, but here's one. We've got 6 data columns. What are our items here? Well, we're measuring int 64 in this one here. Column 0 is going to be distance. It's got a bunch of them in there. Country name for origin. I guess it takes strings as objects. Aircraft group is also an int. And the rest are objects. Okay. Let's use some of the things we learned today in our, what are we calling these? Central tendency. So let's get the mean. Well, yeah. We have the arithmetic mean. How can we get that? Well, we have, pick your library, whichever you want. We could use Scipy, we could use Pandas, we can use, actually, let's just for the heck of it. Well, I will run it first, and then, can someone tell me, using Pandas, how would I get that? How would I get the arithmetic mean of distance using Pandas? You can scroll up and look if you want, or you can have me scroll up. Just someone, can you please tell me how to get the mean of our distance using Pandas? Now, it may help to refresh that Pandas is what's in charge of making our data frames. Okay. So Cole says the following, which should work just fine. I think you put in a little more work than I was expecting. Let's see. All right, so this needs to be capitalized, which is fine. Yeah, so I was going to say just do this instead, but that works just fine. Okay. We've got our arithmetic mean, got our harmonic mean. Very cool. All right, that's step 3. What's step 4? We got to find the median. So here's going to be getting the median from our statistics library. Can somebody tell me what the median, describe to me in English what the median of some data is? Other than Cole, because he already answered 2. The middle. Yeah, that's close enough. It's the item in the middle. What item, given whatever values you're talking about, is the one in the middle of your data? All right, so what is that? Median is 740 miles. All right. What about the, okay, so that's step 4. What about the range? That's step 5. So remember PTP is peak to peak. for NumPy. The range is going to be 9,778 miles, meaning you can expect anything in that range. To our shortest flight to our longest flight has a difference of this. So if we consider our shortest flight to be 0, why would we want to do that? Because let's say I'm calculating fuel costs. Well, the shortest flight we can possibly do is this. So this is our 0 point. All right, from that onward, what kind of range are we talking about? Well, it's about 10,000 miles. What about step 6? Find the interquartile. Where did it go? Here. Of our distance. Looks like that is going to be 968 miles. Does anybody remember what the IQR is? It has something to do with this. And we've got quartiles. Got 1, 2, 3, and 4. So what is the IQR? Yep, it's quartile 3. The value of quartile 3 minus quartile 1. More accurately, it's the 75th percentile minus the 25th percentile. All right, what else do we have? Use descriptive functions from Pandas to get a 5-number summary of distance. Plot a box plot without outliers. Okay, we did that here. So without me, make sure I don't scroll too far. I mean, you have it in front of you, so obviously no spoil. Does anybody remember the name of the function that Pandas has that will give you these 5 values and a little bit more? It gives you 7. Yes, it's describe. It is the method describe with parentheses. So this is the amount of data we have. That's a bunch. Here's the mean, standard deviation, the minimum. That's surprising. That must just be like a... Is it even possible to take off and land within 1 mile? Surely that they just write 1 as they didn't take off. Because like once you take off, even in emergency landing, you gotta do something. I don't know. Anyway, the minimum is 1. The max, look, that's a long flight. Holy cow. Is that possible? So I guess what these mean are including refueling, but I know the US is 3,000 miles across, so I guess this has to be the Trans-Pacific flight. That's a long way. The 75th percentile, meaning if you go 1,300 miles, then you've gone further than 75% of all flights. Very neat. What else? Find the variance in standard deviation. Well, we know a bunch of ways to do that. Oops, I forgot to do the plot. Here we go. So we see the range, we see our quartiles, and we don't have any outliers. So 1303, which is here, 75th percentile. And then 740, which is here, it's 50th. And 335. And for some reason, we have a flight of 1 mile. And I guess it just doesn't want to skew this out too far because this obviously isn't 9,779. But it would be like way up here. It'd be like even further, like up here. Okay. Next, variance, standard deviation. Well, luckily, kind of once you've written the code for these one time, meaning you are, and this is how pretty much every homework and exam and computer science works. Once you can do this once, I don't expect you to do it again. If you can do it once, and this is why it's important to actually do it rather than just copy it or whatever. For like, at least in programming, computer science, you got an algorithm, and your task to the homework is to do it. Okay, I could just go copy and paste it. That's not going to do me any good, because the thing is, once I do it once, now I can just copy and paste it. That's the idea. No one expects you to write this over and over. So we have our standard calculation for variance and standard deviation. We're going to use the statistics package. We could probably use Scipy or whatever we want. Let's see, the variance is, wow. So 1,580,000, no, 6 points, 1,588,667. Now, if we remember, well, I remember some notes we were talking about earlier about how the standard deviation can be a little nicer than the variance, is because it has the same unit. The variance, as far as I know, it is a number. It doesn't have a unit. Meaning, it doesn't matter if your data is in miles or people or IQ points or favorite flavor. It's just a number. But the standard deviation is miles. So this number here, if it were in miles, wouldn't make any sense. But it's not. It's the variance. And this is our standard deviation. And a standard deviation of 1,260 miles makes sense. Now, let's see. I want to just get a regular plot. Let's see if I can remember how to do that. What library is this? PLT is, go away. Sorry, there's a fly. Let's look it up. I want to see if the data looks like it's normal before I do anything silly. No, that's easy. Yeah, it's just that to plot. Let's see, I've got our data frame, which is, what did we call it? Distance? What, maybe? Okay. Now, obviously, this is, what would we call this? Well, the data kind of looks like this. So just from a quick look, I wouldn't say this looks like a normal distribution on the distance. So I can't apply the my standard knowledge of the standard deviation. No pun intended. All right, we calculated the standard deviation though. What else can we do? Last step, show the skewness. Well, it is kind of nice that I plotted this out, because now the skewness should make sense. Based on this, what would you guys say the skewness is? Is it zero-ish, negative-ish, or positive-ish? So Mark says negative. Let's see. Skewness 2.6 and the kurtosis 8.13. So the reason it is positive is because it is heavily skewed to the right. There's some stuff here, but almost all the values are on the right. But no harm in trying. Let's see, what else can I do? I want to do plt dot scatter. All right. Okay, so x okay, this needs to be the name of the column. So this should be distance, right? This I'm not sure what that needs to be. What is our data? Oh well. I was just wanting to tinker around and make a oh, I didn't want to do a scatter plot. I wanted to do a line plot. Oh well. All right, let's take a look at the homework. Very similar to what we were just talking about. We have to read in a CSV file, use some descriptive functions, compute some means of temperature, find the mean of precipitation, median of precipitation and temperature, report whether the temperature has 1, 2, or multiple modes. So if we remember what a mode is, this question should make sense. What would it mean if a temperature had 0 modes? Can someone tell me that? No. If the data set is unique, meaning there's only one value in it, could be many times. There you go. Avery got it. It means that there's no data. The only way that there isn't a mode. So what is the most common occurring data in an empty data set? Well, there isn't one. So the reason I asked that question is because it's an edge case. Edge cases are very important to think about when you're writing software. So this step 5 is about modes. Okay, so I'm going to look at my knowledge of modes. Mode is the most common. How many can there be? Well, there can be as many as there needs to be, really. If every piece of data is unique, then there can be up to n modes. So there can be anywhere from 1 to n modes. It's hard to say in and modes at the same time. But the edge case would be, what if there's no data? If there's no data, there's no mode. Similarly, let's do that same exercise with median, right? So median is going to be the middle value. So what are the edge cases? Well, if there's no data, there's no median. It's pretty simple. The other cases can be is that there is an even number of data points or there's an odd number of data points. There can't be anything else. There's either 0 or there's non-zero, and there's even or odd. If it's even, depending on what is asked, the standard is to take the middle and divide them by the 2 middle and average them. And if there's odd, you take the middle one. Okay, pretty simple. We can do that one more time with, I don't know, standard deviation. What's standard deviation? Well, for all intents and purposes, it's the variance square rooted. And what's going to be our variance? Well, it's going to be a sum of our values minus the average squared over the number. All right. So the edge cases for variance is it the entire sample size? Or is it the entire population size, or is it a sample? Meaning, do I use n or n1, n minus 1? Luckily, you guys don't have to worry about that because you've already written the code once. You pretty much just have to use the functions. Okay, So how many modes does it have? Find the range and the IQR of our precipitation. Oops. Find the 10th, 40th, and 70th percentile on temperature. And if you are paying attention, you will know exactly how to do these. Provide a 5-number summary of precipitation. Plot a box plot without outliers. Interpret it in your own words. So this part should be in English. So you're going to do basically a function call. You need to do a plot and then give some English to say what you see. And then find the variance and standard deviation for precipitation. Find the skewness and kurtosis for precipitation. Okay, now try not to get tripped up and do the task for the wrong column. Easy mistake to make, happens all the time. Other than that, my advice is, if not the exact syntax for everything you need to find, then everything except a plug and play of a variable can be found in the lab. So remember back to, this sounded kind of like the thing we did in the lab, kind of, I don't know. I think it was in the first half, so somewhere in here, somewhere maybe. So go back and look it up. You don't need to be sitting here scratching your head trying to make your own algorithm. There are too many things in data science that you're going to have to do. Well, this is in general in software. There are too many things that you're going to have to make them from scratch every time. Okay, so that's the lab and that's the homework. Does anybody have any questions? I believe there was a question about an exam review. I don't know much about the exam. I do believe that it is going to be Thursday, so there's no lab. And as for review, I don't know. I am assigned to be doing tutoring tonight. So that's about all I know.
Is Dr. Cleveland still in this?
Probably. He might be doing something else, but he's the one who usually shuts it down.
Okay, so last time for exam 1 there was a practice exam. Is he gonna do that for this exam?
No, it's the same modality. There's no benefit to practice. It's just questions and answers, just like last time. Obviously on the newer material.
Okay, so just study notes and lecture.
Yep.
Okay, thank you.
Grace points out they have no links to submit tomorrow for last week's lab.
Actually, they do. They're emerging as we speak.
I see. You spoke and it was answered. Magic. Okay, well, I will be grading a whole bunch, and feel free to email me with questions, comments, concerns.
Okay, so today's lab was supposed to be easy and straightforward. I would suggest you take a look at it because there's elements of it that will appear on the exam on Thursday, but nothing too surprisingly new. And that's about all I have. I'll see you all Thursday morning. This Thursday.
Okie dokie.
Yes. Yes, the in-class exam is scheduled from 8 o'clock to 9:20 as per usual. It's 25 questions, just like last time, different questions. And then there's a take-home component that will most likely be available at 9 a.m., maybe 9:30, and you have 48 hours to complete that and upload it to the server.
Good luck, everybody.
And Grace is asking, do we get multiple attempts for the in-class version of the test? Yes. You get to try everything, depending on your speed, you get to do everything more than once if you want to. Although generally that's a bad idea. if you kind of figure out what's going on, and you shouldn't change your answers. Because unlike goats and cars, if you change your test answers, you're usually picking the wrong one. So don't always second guess yourself.
The take-home exam one, take-home alibi, that was just for people who,
Those are not for you unless we have an email conversation individually.
okay,
So if you see alibi exams and you don't know what they are, don't even start them, because that puts me in a bad situation. I have to average the two. It's to your disadvantage. So don't do it unless you have prearranged that.
okay, thank you.
All right, that's all I've got. I'm going to turn off the recorder and